This is the 20th video in a series covering complex analysis, and today we're going to look at singularities of analytic functions. So let's start with the definition. So a point z0 is called an isolated singularity of a function f of z if f of z is analytic on the punctured disk of radius r for some r bigger than 0 centered at z0. So what I mean by the punctured disk is that it includes all of the points inside of the disk except for z0 itself. So there are three main types of isolated singularities, but before we dive into this, I'd like to look at some examples of isolated singularities and non-isolated singularities. So let's first look at an example of an isolated singularity. So here if we take f of z equals 1 over z minus 1 times z minus 2, this thing has isolated singularities at z equals 1 and z equals 2. And why is that? Well, that's because we can find a punctured disk around each of these points on which this function is analytic. And so for the case z equals 1, maybe we would take a disk around here with radius 1/2. And for z equals 2, well, let's maybe go ahead and take a disk around that also with radius 1/2. So that would be a good example of each of those. So that would be our radius. Although I think we could take the radius up to a radius of 1 for each of those, because all that we need to make sure of is that we don't get up to the other singularity. Okay, so that's an example of a function with an isolated singularity. Now let's look at some with non-isolated singularities. So we'll look at two examples of functions with non-isolated singularities. The first one is f of z equals the square root of z. And the second one is, well, I'll call it g of z, which is the principal branch of the logarithm, so log z. Let's recall that both of these are analytic on the entire complex plane minus the ray between 0 and minus infinity. So maybe we would write this as the ray minus infinity to 0 along the real axis. So maybe we could make a picture of it like this. So this would be the region on which this thing is analytic. We have to take out the origin, and then we take out the negative real axis like this. And then let's note that z equals 0 is a non-isolated singularity. So we'll say z0 equals 0 is a non-isolated singularity. And why is that? That's because if we take a radius of anything around z equals 0, and this could be any radius at all, it will most definitely include some points right here on which the function is not analytic. So not analytic here. And that's kind of by stuff we had done in previous videos. Okay, so just to reiterate, that makes z equals 0, in other words, the origin, a non-isolated singularity. Okay, so now that we've looked at some examples of isolated and non-isolated singularities, what I'd like to do now is build up the following three definitions of types of singularities. So removable singularities, poles of order n, and essential singularities. So let's note that if f of z is analytic on this punctured disk, that tells us that f of z has a Laurent expansion on that punctured disk. So in other words, f of z can be written as the sum as n comes from integers of a sub n, and then z minus z0 to the n. So I like using this notation where n comes from the integers, but this could also be written as n equals negative infinity to infinity. So it's a potentially doubly infinite sum in both directions. And then furthermore, we know that this expression is valid on this punctured disk. So all values where z minus z0 is less than r, but strictly bigger than 0. And so that's by some stuff that we did on the last video where we discussed Laurent expansions of analytic functions. Okay, good. So from this expansion, we can build these three definitions over here, but let's fill in some blanks. So we need to put where f of z is equal to the sum as n trends over all integers of a sub n and then z minus z naught to the n on the punctured disk z minus z naught between 0 and r, like this. Okay, so z naught is called a removable singularity if a sub n is equal to 0 for all n less than or equal to -1. So why is this a removable singularity? Well, let's notice if we do the expansion here, we'll get f of z equals a naught plus a1 times z minus z naught to the first power plus a2 times z minus z naught to the second power, and so on and so forth. So we don't have a z minus z naught in the denominator of any of these terms. So that means we should be able to quote unquote plug in z naught with no problem at all. And in fact, if we redefine f of z so that at z naught it's equal to a naught, then we have created an analytic function. So that means in this case, this can be extended to be analytic on the entire disk z minus z naught less than r by setting f of z naught equal to a naught. So I'll just put that we need to set f of z naught equal to a naught for that to happen. So the next possibility is that we do have negative terms, but only finitely many negative terms. That means that there would be a smallest one. And that's this case where we have a pole of order n. So we say that z naught is a pole of order n if a sub minus n is not equal to 0, but a sub little n is equal to 0 for all n strictly less than minus n. So let's see. In this case, our Laurent expansion looks like the following object. So we've got a sub minus n, z minus z naught to the minus n plus a sub minus n plus 1, z minus z naught to the minus n plus 1, and so on and so forth. So it's a pole of order n because that's like the largest power of z minus z naught in the denominator. And this can't be extended to be analytic, but notice if we clear the denominators on the right-hand side, then we have an analytic function. So what about an essential singularity? Well, that's the case that we haven't covered yet. And that would be if we have infinitely many negative powers of z minus z naught. So we could write that as follows. So if a sub n is not equal to 0 for infinitely many n which are less than or equal to -1. So in this case, it really means that we need all of the negative powers. So all negative terms, maybe a minus n, z minus z naught to the minus n. And I don't really mean all of them. I just mean we need to go infinitely kind of down into the negative direction. Okay, so that's a nice classification of these types of removable singularities, poles, and essential singularities. Now we're going to prove some results. But before we do that, I'd like to include one more definition over here. So I'll sneak it in right here. And this definition kind of follows from some stuff that we did last time. And this would be what it means to have an isolated singularity at infinity. So we say that f of z has an isolated singularity at infinity if f of 1 over z has an isolated singularity at z equals 0. Okay, so that's the standard way for defining things at infinity in the realm of complex variables. And that indeed means that we can check for singularities at infinity pretty easily just by looking for singularities at 0 for this kind of companion function here. Okay, so now that we've got all of these definitions taken care of, let's look at examples of each of these types of singularities before we prove some results. Okay, so now let's look at 3 examples. So in these 3 examples will give us examples of all of these types of isolated singularities. We'll start with the function cosine of z minus 1 over z. So let's notice that we can expand cosine as the sum as n goes from 0 to infinity of minus 1 to the n over 2n factorial times z to the 2n. And then from that, we subtract 1 over z, because we've got that z down there. But what does subtracting 1 do? Well, notice the very first term of this sum is 1. So that just turns this starting term from 0 to 1. So that means we have the sum as n equals 1 to infinity minus 1 to the n over 2n factorial z to the 2n, but now that's all over z, so we can do z to the 2n minus 1. But now we can expand that out a little bit. So let's notice the first term now will be negative 1 over 2 factorial, so that's negative half. And then we'll have z to the 2 minus 1, so that's z. Now the second term will be plus 1 over 4 factorial, so that's 24, and then we'll have z cubed, and then plus dot, dot, dot. So let's observe that that doesn't have any negative powers of z. So that means that z equals 0 is a removable singularity. So z equals 0 is removable. And we can see that we could redefine this function to be equal to 0 at z equals 0. And we would indeed recover some sort of analytic function. Okay, so let's look at this next one. We've got z cubed over z minus 1. So first we'll notice that z equals 1 is some sort of singularity because it gives us a 0 in the denominator. And since we've got z minus 1 to the first power, it stands to reason that this really should be a first order pole. But let's see how that works out with the Laurent expansion. So in order to do that, let's take this numerator and write it in terms of this denominator. So we've got z cubed. So that means we need to write that as z minus 1 cubed. So that's going to take care of the cube term of z, but notice that we've included a z squared, a z, and a constant term in that we've got to take care of. So if we add in 3 times z minus 1 squared, then we'll cancel out the minus 3z squared term that we pick up here. But then we also pick up a minus 6 times z. Well, this one picks up a plus 3 times z, so that means now we have an additional negative 3 times z. So we can take care of that by adding 3 times z minus 1. But now let's check the constants. This gives us a negative 1. This one gives us a plus 3, this one gives us a minus 3. So the plus 3 and the minus 3 cancel, meaning that we just need a plus 1 here. So that's like the expansion of this numerator in terms of this denominator, if you will. Now we have this is all over z minus 1. But now we could rewrite that as 1 over z minus 1. That's this term right here, plus 3. That would be this term right here. And then plus 3 times z minus 1, and then plus z minus 1 squared. So that would be like our version of a Laurent expansion centered at z minus 1. But seeing that the smallest power of z minus 1 is to the negative first power, that tells us that this is a pole of order 1, or that's sometimes called a simple pole. Okay, so simple pole at z equals 1. So let's maybe also notice that something's happening at z equals infinity as well. because we've got this z cubed on the top, which means as we let z approach infinity, this will approach infinity. But let's maybe check that we indeed do have a singularity at z equals infinity by this definition over here. So in order to dive into the singularity infinity, we want to replace z with 1 over z and then look at the resulting function's singularity at z equals 0. So let's see, this gives us 1 over z cubed over 1 over z minus 1. So maybe from here, we would like to multiply the numerator and the denominator by z. So let's see what that'll give us. That'll give us a 1 over z squared in the numerator, and in the denominator, we'll have 1 minus z. But now we can expand that denominator as a geometric series. And that's going to give us 1 over z squared times the sum as n goes from 0 up to infinity of z to the n. That means that here we get 1 over z squared plus 1 over z to the first plus 1 plus z squared. Now notice that means that this transformed function has a pole of order 2 at 0. So that's sometimes called a double pole. So double pole at z equals 0. But that means our original function has a double pole at z equals infinity. So I think I misspoke and thought that there might be a triple pole, but there is a double pole. So let's just maybe summarize this. So this function right here is a double pole at z equals infinity and a simple pole at z equals 1. So that's a complete classification of the poles of this function. So now let's look at this guy right here, e to the 1 over z. So we haven't covered any examples with essential singularities, so this should probably have an essential singularity. And we'll see that it does. And we can see that by just taking the standard expansion here. So this is the sum as n goes from 0 to infinity of 1 over n factorial, and then 1 over z to the n. So that expands out as 1 plus 1 over z plus 1 over 2z squared plus 1 over 3 factorial, which is 6z cubed plus dot, dot, dot. So notice there will be infinitely many terms that have z's in the denominator here. So that means that this is an essential singularity at z equals 0. So essential singularity at z equals 0. So now we've covered examples of all of these types of isolated singularities, and we're ready to move on to some results. So for our first result, which is sometimes called Riemanns Theorem, we will suppose that z0 is an isolated singularity of f, and that'll be actually a pretty standard setup for all of these results today. And then we'll prove that if f of z is bounded near z0, then z0 is a removable singularity. So this is a nice classification of when we get a removable singularity. Okay, so let's get started. So we're going to start by writing f of z via its expansion. So we know it expands as a Laurent series, which is the sum as n goes over the integers of a sub n z minus z0 to the n. And this is valid for z within R of z0, excluding the value where z is equal to z0, so that punctured disk. And so next we're going to take some r such that r is between 0 and r, and then we'll take m to be equal to the maximum of f of z, or I guess I should say the modulus of f of z, on the punctured disk with radius little r. So I'm going to write it like this. So we've got 0 is less than the modulus of z minus z0, which is less than or equal to little r. And so we're able to know that this sort of maximum exists because we have f of z is bounded near z0. Okay, so we'll start by choosing little r, where it's between 0 and big R. And now we'll use the fact that f of z is bounded near z0. So that means we're also going to take m to be a positive real number such that the modulus of f of z is less than or equal to m whenever z minus z naught is between 0, not including 0, and less than or equal to this little r. So again, we're able to do that because we have this boundedness condition on our function. Now we're going to look carefully at the coefficient an here. And in fact, we're going to look at the modulus of this coefficient. So the modulus of the coefficient an is equal to the modulus of 1 over 2 pi I, and then the integral around this circle, z minus z naught equals r of f of z, over z minus z naught to the n plus 1 dz. So if you remove the modulus from both sides of this equation, you just get the formula we developed in the previous video for the coefficient a naught itself. Now we'll use this boundedness fact of f of z here, as well as the fact that z minus z naught is less than or equal to r. And that means that we have all of this is less than or equal to 1 over 2 pi. Here we took the fact that the modulus of I is equal to 1 of the integral around this circle, z minus z naught equals r of m over, let's see, r to the n plus 1 dz. So again, that's just from taking those bounds there. But integrating this, which is just a constant, will give us the circumference of that circle, which is 2 pi r. So since that's 2 pi r, that'll cancel out one of the r's in the denominator as well as this 2 pi. So that gives us m over r to the n. But next, let's notice that if n is less than or equal to -1, then we really have m times a positive power of r. And that's important because in that case, as r trends off to infinity, we see that m over r to the n trends off towards 0, which means the modulus of a sub n equals 0, which means a sub n equals 0. And that's true for all n less than or equal to -1. But that's exactly what we need to have a removable singularity. Okay, so our next result will have to do with poles of order n. So like I said, our next result will involve poles of order n. And in fact, we're going to show that 3 conditions are equivalent. So that's what this means. The following are equivalent. So the first is that z naught is a pole of f of z of order n. So what I haven't written here is that z naught is an isolated singularity. But like I said, that's our setup for all of these. So that's the first statement, z naught is a pole of order n. The second statement is that if we define a function g of z as z minus z naught to the n times f of z, that new function is analytic at z naught. And furthermore, it is non-zero at z naught. Then finally, 1 over f of z is analytic at z naught, and it has a 0 of order n. Okay, so let's see how this goes. So the first thing that we'll do is prove that 1 is equivalent to 2. And so let's maybe start with this forward direction. So let's suppose that z naught is a pole of order n. But if z naught is a pole of order n, that means we can expand it as a Laurent series starting at -n. So we've got the sum as lowercase n goes from -n to infinity of a sub n z minus z naught to the lowercase n, and I should point out here that a sub -n is not equal to 0. That's built into the definition over here of a pole of order n. So now let's look at our function g of z, which, like I said, is going to be this z minus z naught to the n times f of z. But what is its power series expansion? Well, we can just do standard arithmetic rules, and we'll see that this is the sum as n goes from -n up to infinity of a sub n, and then z minus z naught to the capital N plus little n. Now we're going to re-index this thing. So now we'll do a re-indexing step. So let's replace lowercase n with lowercase n minus capital N. So let's put a box around that to show that that is the re-indexing that we'll do. So that means our starting point will no longer be negative n. Our starting point will now be 0. So that's going to give us the sum as n goes from 0 up to infinity of a sub n minus n and then z minus z naught to the, let's see, lowercase n. But now we see that this is most definitely analytic at z naught. We can see that it's analytic at z naught because it doesn't have any negative powers of z minus z naught because of our reindexing. Further, we can note that g evaluated at z naught will be equal to a sub minus n, which is not equal to 0. That's by our construction over here. So that's exactly what we need for part 2. We've got that it's analytic by that expansion, and we've got that it's non-zero from this. Okay, so now let's maybe move on to the reverse direction. So we're going to start by supposing that g of z, which is z minus z naught to the n times f of z, is analytic at z naught and it's non-zero at z naught. But if it's analytic at z naught and non-zero there, that means it has a Taylor series expansion about z naught, where the first term, or the 0th term, if you will, is non-zero. So to put that all down, we've got g of z is equal to the sum, as n goes from 0 up to infinity, of b sub n, and then z minus z naught to the n, where b sub 0 is non-zero. But now we'll look at f of z. And so f of z will be g of z over z minus z naught to the n, just by like sort of solving this thing for f of z. That's pretty easy to see. But that's going to be equal to the sum, as n goes from 0 to infinity, of bn, and then we'll have z minus z naught to the n minus capital N. Now we're going to play the same game that we did up here, but we'll just re-index in the other direction. So let's take n and replace it with lowercase n plus uppercase n. So that'll be our re-indexing here. So that means our sum will now start at n equals negative n. So n equals negative uppercase n to infinity of b of n plus n, and then we have z minus z naught to the n. And let's notice the first term here is non-zero just by our construction up here. And so that proves that this first statement is true based off of the definition of a pole of order n. Okay, so that's maybe 1 implies 2 and 2 implies 1. Maybe I'll leave it as a warm-up exercise to show that these are also equivalent to 3. This is pretty straightforward given what we've done here. So now we'll move on to another result involving poles. So next up, we've got another sort of classification type theorem for when an isolated singularity is a pole. In particular, we'll show that an isolated singularity z naught of f of z is a pole if and only if the limit as z approaches z naught of the modulus of f of z is equal to infinity. Okay, so we've got an if and only if statement here, which means we've got 2 directions to prove. Let's start by proving this forward direction. So we'll suppose that z naught is a pole of f of z of order n. So we might as well assume that it's got a certain order so we know how to write down it in terms of what we had previously. Okay, so our previous theorem means that f of z is equal to g of z over z minus z naught to the n, where g of z is analytic at z naught and g evaluated at z naught is not equal to 0. Now, by the fact that g of z is analytic at z naught and g of z naught is equal to 0, that means that for z near z naught, so within some sort of delta neighborhood, if you will, we have the modulus of g of z is bigger than m, which is strictly bigger than 0. So in other words, since it's non-zero there, it does not have a 0 at z naught, we can bound it away from the number 0. Okay, so that's good, but now we're pretty much ready to do it. So let's notice that the limit as z approaches z naught of the modulus of f of z can now be written as the limit as z approaches z naught of the modulus of g of z over z minus z naught modulus to the capital N. But that's going to be bigger than or equal to lowercase m times the limit as z goes to z naught of 1 over the modulus of z minus z naught to the n. But that's clearly equal to infinity by some limits that we did previously. Since this denominator is approaching 0 and the numerator is fixed at 1, or maybe it's fixed at this non-zero number m, that clearly goes to 0. Okay, so now let's do the reverse direction. Now we're ready for the reverse direction. So let's suppose that the limit as z approaches z naught of the modulus of f of z naught equals infinity. But that's equivalent to saying that the limit as z approaches z naught of 1 over the modulus of f of z equals 0. Sorry, that should be the modulus of f of z there. Okay, but that limit being 0 means that we can find some radius r such that 1 over f of z is analytic on this punctured disk. So 0 is less than z minus z naught, which is less than r. And why is that? Well, we just really want to bound our z away from any 0 of our function f of z. Since we're analytic on this disk right here, this punctured disk, that means we can expand it as a Laurent series on that punctured disk. So we can expand 1 over f of z as the sum, as n goes over all integers, of a sub n z minus z naught to the n. But now let's take the limit of both sides here. So I'll just do it like this. So this is the limit as z approaches z naught. And on the left-hand side, we get 0. But then on the right-hand side, this is only 0 if a sub n is equal to 0 for all n less than or equal to -1. But what does that mean? That means that at most 1 over f of z, which I'll rename as g of z, has a removable singularity at z naught. But if it has a removable singularity at z naught, it can be extended to an analytic function at z naught. So extended to analytic at z naught, but it's already analytic on that punctured disk, so that's going to be on the disk z minus z naught less than r. So we've called that extension g of z. The notation here is a little bit squirrely, but I think we've said it carefully enough. Now g of z actually has a 0 at z naught, and that's because this in fact needs to be less than or equal to 0 in order to get a 0 over there on the right hand side. So if g of z has a 0 at z naught, and g of z is analytic on that disk, then that means it has a 0 of a certain order at z naught. So let's suppose that g of z has a 0 of order n at z naught. But what does that mean? That means that g of z can be rewritten as z minus z naught times h of z, where h of z naught is not equal to 0. That's by something we did a couple of videos ago. But that means that f of z equals, let's see, 1 over h of z all over z minus z naught to the n. And by our construction, this 1 over h of z is analytic at z naught, and it's non-zero at z naught. That's by this right here. But we've got this z minus z naught to the n. That means that f of z has a pole of order n at z naught. And that finishes this proof. Okay, so we're going to finish this video with one more result that regards essential singularities. So let's notice we've had a result about removable singularities. That had to do with extension to an analytic function. We've had a couple of results about poles of order n, so that means what we're left with is a result about essential singularities. So we've got one more result, and like I said before, that involves essential singularities, and this is in fact called the Ksarati Virustras theorem. So it's a pretty classic result. And it really proves like how strange essential singularities are. So let's see what it says. So it says that if z0 is an essential singularity of f of z, then for all w in complex numbers, we can find a sequence of complex numbers zn such that the limit of the zn goes to this essential singularity, but the limit of the function values of that zn goes to w. So the important thing here is that for all w in C. So for all w in C, we can find a sequence where that sequence approaches the singularity and the output of the function approaches anything we want. So again, this sort of tells us how crazy this essential singularity is. Okay, so let's get into the proof. This is maybe the standard proof, which is given by a contrapositive. And so that means we want to assume that the conclusion is not true and then prove that the hypothesis is not true. So let's suppose that we have something which I'll call W0 in C such that all sequences Zn, which are sequences of complex numbers, such that the limit as n goes to infinity of Zn is equal to Z0, we have the limit as n goes to infinity of f of Zn is not equal to W. So that would be the negation of this conclusion here, just if we negate that conclusion really, really carefully. Okay, but from here we're going to jump out of the sequence world, but how we jump out of the sequence world is allowed because of our construction right here. Okay, so what does that tell us? So all of this tells us that there exists some epsilon which is bigger than 0 such that for all z that are within R of z0, we have the distance between f of z and w is bigger than or equal to epsilon. So saying something does not converge via a limit means we can bound it away from that potential limiting value or that non-limiting value, if we will. And so that's what we have here. So let's notice that generally when you prove something has a limit, you have a for all epsilon and there exists a delta. But here we have a there exists an epsilon such that for all r, and this is z minus z0 less than some r. And now from here, we're going to define a new function, and we'll call that new function g of z. And that's going to be 1 over f of z minus w. Why do we want to look at that? Because we've bound this f of z minus w away from 0, which means we've bound this g of z away from infinity, if you will. So in other words, we have the modulus of g of z is strictly less than m, or maybe less than or equal to m, where we take m to be 1 over epsilon. And this is going to be for all z minus z0 less than r. So like I said, we bound it away from infinity. We've like bound it, for instance. But that means that the limit can be infinite, which means in fact we have a removable singularity at z0. So like I said, g of z has a removable singularity at z0. But that means it can be extended to an analytic function. Extend it to analytic on z minus z0 less than r. And I realized this should have been a punctured plane before we did this extension. But then if g of z is analytic here now, then it might have a 0 of a certain order at z0, and that 0 could be of order 0 if you want. So let's say that g of z has a 0 of order n, which is bigger than or equal to 0 at z naught. So a 0 of order 0 is just really not a 0, but still we want to keep that in there. But that means that we can take g of z and rewrite it as h of z times z minus z naught to the nth power. And that's by something we did in a previous video. And furthermore, we know that h evaluated at z naught is not equal to 0. Okay, so now from here, we can take f of z and solve it in terms of h of z and all of this other stuff. So I'll let you guys check that I make the right calculation, but what it turns out to be is 1 over h of z plus w times z minus z naught over z minus z naught to the nth power. Okay, so that's what we get for f of z. But just by the look of this, we know that 1 over h of z is analytic at z naught. That's because h of z naught is not equal to 0, which means that this f of z has a pole of order capital N bigger than or equal to 0 at z naught. So a pole of order 0 would be like a removable singularity. A pole of order bigger than 0 would be just like a pole like we define over here. But that means the singularity that we have is either a removable singularity or a pole, which means it's not an essential singularity. So we have z naught is not essential. But that is the negation of our hypothesis up here. So we just proved that the negation of the conclusion implies the negation of the hypothesis, which is the contrapositive to this statement. But the contrapositive is logically equivalent to this statement. And so that finishes the proof of this theorem. Okay, so let's finish off with me giving you guys some warm-up exercises. So here I've got 2 warm-up problems, one which has a couple of parts. So the first is to finish off that proof of the theorem that we didn't quite finish, and that is that f of z has a pole of order n at z naught if and only if 1 over f of z has a 0 of order n at z naught. And then the second is to find and classify all of the isolated singularities of these 4 functions. So we have z minus 1 over z squared plus 1 squared, e to the 3z minus 1 over z, z times sine of 1 over z, and finally z over e to the 1 over z minus 1. And recall that we've got more machinery than we did when we did those first examples at the beginning of the video. In fact, if we have singularities that are poles, we can easily describe their order by one of those theorems that we had before. Okay, that's a good place to stop.